So this lesson is going to be on chemical potential energy diagrams. The content for this lesson is pretty much the same, whether it's the AP exam that you'd be writing or the Alberta Chemistry 30. So I have a reaction, hydrogen gas plus iodine gas makes hydrogen iodide. And let's say that this reaction, under some conditions, releases 100 kilojoules. When 1 mole of hydrogen reacts with 1 mole of iodine. Now there's certain notation, the notation that we're going to use to express the release of 100 kilojoules. So this release of 100 kilojoules means that there is less energy in the chemicals at the end than there was at the beginning. So one way to start discussing with this is there'd be some potential energy at the beginning. This potential energy would be made up of the hydrogen and the iodine. At the end, there'd be some potential energy. And all that potential energy would be from just the one chemical, hydrogen iodide, but there's 2 units of that. So you have a certain amount of potential at the beginning, potential at the end, and we have a release of 100 kilojoules net. Now this potential energy, a better way to think of what type of energy it is bond energy. So in chemistry 20, you would have studied covalent bonds, single bonds, double bonds, triple bonds. There'd be energy in those bonds. That is a form of potential energy. So at the end, there is less energy at the end. The difference in potential energy is something that we call enthalpy, which is given a symbol H. E is already used for straight up energy. So enthalpy is symbol H. And this is going to be a change in enthalpy. So the difference in potential energy from the end to the beginning is a release of 100 kilojoules. So the change in enthalpy is 100 kilojoules. And then this release is a loss of energy or loss of potential energy, and that will show up as a negative sign. So there's 100 less kilojoules of potential energy at the end than there is at the beginning. Now in chemistry 30, we just assume that this is 1 mole of hydrogen, 1 mole of iodine, making 2 moles of hydrogen iodide. In AP, they explicitly state that this is minus 100 kilojoules when using molar amounts or per molar amounts. So in the AP lessons, I'll put in the per mole. When we do chemistry 30 content again, I will not put in the per mole. So let's take a look at what this information looks like on a chemical potential energy diagram, which is the theme of this lesson. So we have a reaction coordinate axis and a potential energy axis. So starting to label, at the very beginning, our chemicals are going to be at a certain amount of potential energy. We're never really going to know exactly what this potential energy is. It's very difficult to measure the enthalpy or potential energy at the beginning. But the very beginning would be our hydrogen plus our iodine. I'm going to leave out the states to make things a little cleaner. At the end, we know that there's 100 kilojoules for every mole reacting less, or per molar amounts less. So I've kind of preset, let's say each line is 100 kilojoules per mole. This is kilojoules when using molar amounts. So I just kind of made up. We don't really know this. This wasn't in the information at the beginning. Let's say we're at 200 kilojoules of potential energy. We've lost 100, so we would be at, From 200 down to 100 is where our products would be. Now we need the count. It doesn't matter. If we had half the chemicals, we'd have half the energy change. So we have 2 moles here. So this is our potential energy at the beginning, potential energy at the end. This drop, the difference between the beginning and the end, is our change in enthalpy, which is our minus 100 kilojoules per mole. Again, it's better thought of as 100 kilojoules are released when 1 mole makes 2 moles. That's the meaning of the per mole. So this axis isn't time, it's reaction coordinate. It is what is the coordination of the bonds over time. And I want to fill in this middle part, and that's what we're going to be studying in this lesson and in a bit more depth in the next lesson. As the reaction starts, you need to put some energy in. Reactions don't just happen all on their own. There's an input needed. If you think of a fire triangle, you need a fuel and you need a spark to get it started. So that energy being put in to get the reaction going would show up as an increase in energy. Then the new chemicals can be formed, energy gets released, and you end up at whatever the enthalpy is of the products. This very top part is referred to as the activated complex. We don't always know exactly what this looks like, but this would be the maximum potential energy. So imagine you've got hydrogen, and you've got iodide. And at some point, you've got some bonds starting to be formed between the HI, and these bonds are starting to break. So this is kind of the best visual I could give of what the activated complex looks like. It's a very high energy complex. It is the top of your chemical potential energy diagram. So the total energy required to get this reaction started would be this red line that I'm putting in. And this is referred to the energy of activation, E sub A. So using the scale that I have used, we started at 200, we're up to 400 kilojoules per mole. So the activation energy would be 200 kilojoules for this particular reaction as drawn. Activation energy is always positive. It is never negative. You always have to put energy in. The products, the energy of the products can be lower than the beginning or higher than the beginning, but the activation energy will never be a dip at the beginning. You never remove energy to get the reaction started. It is always an input. So we have the key pieces of our chemical potential energy diagrams. I'll quickly recap them and then we'll build upon this in the next slide. So we have enthalpy change, the difference between potential energy at the beginning and the end. It is symbol H. Okay. Some diagrams, enthalpy and potential energy are often used interchangeably. When we get into the AP thermodynamics section, I'll go into a little bit more detail, but the best way of thinking of what is enthalpy, it is potential energy, difference in enthalpy, difference in potential energy, it is the drop. You need to be familiar with the term activated complex and more importantly, the activation energy. Whenever energy is released, like we had in this example, we would refer to the reaction as being exothermic. Okay. You can feel that heat if you are actually carrying out the reaction. So exo in chemistry is always a out prefix, thermic energy. So energy is coming out. So from the perspective of the system or the chemicals, they have lost energy. There's a loss in energy when heat is released. Endothermic reactions are when energy is put into and stored as extra potential energy in the products. So this is when heat is absorbed and the system has gained energy. Now you might think, oh, it's gained energy to be hotter, but no, it's gained potential energy. Energy has to be conserved, so there's going to be some loss of energy kinetic from the surroundings. So in an endothermic reaction, if you touch it, it's going to be taking some kinetic energy from your hand. Your hand is going to feel cooler as it's lost kinetic energy and it's been stored in the bonds. So next we'll look at reversible reactions and what catalysts do to reactions. So I'm just going to use a generic reaction for this second slide. Imagine there's some chemical AB, and it's going to decompose into, let's say these are diatomics. So we get a couple A's and a couple B's, so we need two of that, and I'm going to assume that the change in enthalpy is positive now. So this is going to be an endothermic reaction. Okay. There's going to be more potential energy at the end than there is at the beginning. So we'll see what this looks like, and we'll look at what are the characteristics of the reversible reaction and what does a catalyst do to the diagram. So we have potential energy again, kilojoules or an AP, kilojoules when we use molar units. I'll make each of these 25 this time. So there has to be some starting enthalpy. This is something that we never measured. It would just be something given to us. So let's say the original enthalpy is 50 kilojoules per mole. So this would be 2 of our AB chemical. We know that the change in enthalpy is positive in this example. So that means energy was released. There is more, energy is absorbed. There is more potential energy at the end than there is at the beginning. So we know for sure that there'll be a higher potential energy for our products. Now when I put in the activation energy, okay, we're going to have to put energy in to break A and B apart. We're going to have to put in more energy than the products. We're not sure how high it is, but I'm going to go up to the 150 kilojoules and then down to our products. So this is our activated complex and our energy input. Is that dotted arrow. So this is our E sub A. So it's going to 150, started at 50. So this would be 100 kilojoules would be our activation energy. What is our enthalpy change? Well, it's from the beginning to the end. So we started at 50. We went to 100. This is our change in enthalpy. Now, I always like to put a sign in this type of thermodynamics or in this rate section. So the positive means energy is absorbed, and we have 50 kilojoules per mole absorbed. So 50 kilojoules are going to be absorbed when 2 moles of chemical AB react to make 1A squared and 1B squared. Okay, so that's the meaning. This per mole, again, just means when you use molar amounts. So I'm going to do a little bit of a summary. I want to talk about forward. Then we're going to look at what if this reaction went backwards. We've got our change in enthalpy, and we've got our activation energy. Well, we've already done the numbers for the forward. The enthalpy change is 50. This is kilojoules per mole. The activation energy was 100. What about in reverse? Okay, so hopefully you've done the equilibrium unit, or you can remember the reversibility of reactions from equilibrium. So a squared and b squared could go backwards and make 2ab. If you go backwards, you're starting from higher enthalpy or potential energy to lower, so that'd be exothermic. It would be a drop in energy, so the reverse enthalpy change is the exact same size, but it is down. So that would be minus 50 kilojoules per mole. What about the activation energy? Is it just the reverse? Well, no, it's not. We're not just flipping it. We have to look at what is the barrier. So that'd be from where we start. So that'd be at our products to the high point. So the E sub A reverse would be this blue arrow. So it goes to 150 again, but it starts at 100. And in this case, the activation energy would only be 50 kilojoules per mole. So the enthalpy change always just flips the signs forward to reverse. The activation energy, you have to re-look at the diagram and recalculate it. There's no way just looking at the data for the forward that you can predict the reverse without a graph. You would need a graph for the enthalpy change. So that's forward and reverse. You're just looking in the forward direction or the reverse direction. Last, what does a catalyst do? So the black line that I've put in would be for no catalyst. What a catalyst is going to do is lower the activation energy. So I'll dash this in green. We're going to go to a less high, a lower barrier. So I put a little dot in. So a catalyst is going to cause a different pathway. You're still going to start with your reactants. You're still going to end up with your products. But a different line, a different path, a totally different mechanism, and a bunch of steps to get from the beginning to the end. The activation energy with a catalyst will always be lower. So the activation energy, it's going to maybe 120 from 50, so it's about 70 kilojoules in this case. Okay. And that is the trend always for a catalyst. A catalyst could never have a pathway that goes higher. That would actually be an inhibitor to the reaction. It would not meet the definition of a catalyst. A catalyst is something that speeds up the reaction, though it is not consumed. So that's the main topics for chemical potential energy diagrams. You should be able to draw them when they're endothermic, sort of higher at the end, exothermic, lower at the end, activation energy. You should be able to draw a pathway for a catalyst. You should be able to, if you're giving a diagram, predict the activation energy and enthalpy change in both the forward and the reverse direction. Last little thing, this is a diagram you'd probably never be asked to draw, but I really want to emphasize the law of conservation of energy and what's really going on throughout our reactions. So if I plot total energy now, again, this is something you'll probably never do, that total energy would need to be fixed. It is not going to change. Now that total energy might be made of different amounts of potential and kinetic. So at the very beginning, let's say this is our energy potential, and everything above this is our energy kinetic. Okay. So if you think of a chemical, imagine you've got water and you're going to decompose water. There's potential energy in the bonds, but then the water has a certain temperature. That's kinetic energy. So the hotter it is, the more kinetic it has, and you're going to have a certain total. In a reaction, if water is decomposing, that's endothermic. So you're going to have an increase in potential and then a drop down. And you get your products. Now everything sort of on the lower half of this diagram represents our potential energy. So the total potential is all of these black dashed sections. Okay. At the same time, if you wanted to talk about kinetic, which we almost never do, that would just be what's going on in the top section. As potential goes up, kinetic goes down, and vice versa. Now, when we get into the next unit, at least in the sequence that we're doing it, when we get into thermodynamics, we would probably want to know the difference between potential at the beginning and potential at the end. We would want to know the change in enthalpy, which is the change in potential energy. Now, we can't actually measure potential energy, okay? But we can measure kinetic fairly easily. Okay? In Alberta grade 10, we learned that you can measure heat in grade from the mass, the C, and the delta T of whatever substance gets that thermal energy. So we can actually solve, not for delta H, but we can solve for the change in kinetic and relate that back. Okay? So this potential energy in the black is often referred to as our system. Okay. So our chemicals. So black, they have a certain amount of potential energy. There's surroundings around the chemicals. Okay. The surroundings are going to be a certain temperature, they have kinetic energy, and we're just going to have this exchange of energy. The system can lose energy and make the surroundings warmer, or the system can gain energy, make the surroundings cooler, but the total energy is always the same. Again, just want to highlight that energy total is this exchange of potential and kinetic. Don't be expecting to draw something like this. Just realize that's always true. Last, just wrapping up a little bit on catalysts. Catalysts can be put into a few different categories. You can have one state, a homogeneous catalyst. So this might be a reaction where everything is aqueous. So we have aqueous chemicals, and the catalyst would also have to be aqueous. Okay. In many cases, you have a heterogeneous catalyst where it is a different state than the reaction. So in a heterogeneous catalyst reaction, there's going to be 2+ states. Okay. So maybe you have a aqueous reaction, but the catalyst is a solid. That would fit into the heterogeneous category of catalysts. Okay. So if you're given a chemical reaction, just look at the state of the catalyst compared to the other chemicals. If there's any mix match at all, it's going to be in the heterogeneous section. And then we're not going to really dive into this, but there's a huge group of biological catalysts that are called enzymes. Very complicated. We don't know how a lot of enzymes work, and somebody might spend 5 years of their life doing their PhD just trying to understand a bit about how one enzyme works. So we've got these 3 categories you should be able to recognize: biological, and then sort of tabletop chemistry, the homogeneous and heterogeneous catalysts. So review for this section from the Advantage AP Chemistry 2 book is as follows. Okay. This is the second last lesson of this unit. The last lesson will look at reaction mechanisms. I kind of drew a nice smooth curve between the beginning and the end. this black line or the dotted green, often there's more than one step between the beginning and the end. So we're going to break down and look at a more complicated picture of the beginning to the end. This material would be advanced placement only and is not something that would be covered in regular 30.